Hi students, so in this video we are going to be starting chapter 2. So this is just part 1, and in part 1 we cover atomic theory, the discovery of protons, neutrons, electrons, and then just give a view of what the atom looks like. So the first thing you want to do is watch this TED video. This is a nice short clip, just basically showing how the atom was discovered. And what I'm going to go through in this slide deck here are a couple laws that they don't talk about, and then a couple other key experiments they don't discuss in there. Okay, so the first law we need to cover, and all of this is just to set a foundation for you guys going forward in the class. The first law is the law of mass conservation, which basically says if you start out with reactants, basically chemicals that you want to mix before a reaction occurs, there's a certain mass to them, and at the end of the reaction, you'll get something new, but the mass should be the same, and it will be the same total. The only time you might see some mass kind of disappear is maybe if it was evolved as a gas. That's kind of the only thing that you might not capture, but still mass was not destroyed in that. So here's a solution of lead nitrate. It's colorless. Sodium chromate solution, that's yellow. When you mix these two, what you get is this mixture here. You have a solid precipitate, lead chromate, and you also have a solution in there, still a liquid, and what's in there is both water and sodium nitrate. So those are ions. We'll talk more about aqueous solutions later, but the whole point is the mass is the same. Mass is neither created nor destroyed. Here's how you could use it. Say you started out with 100 grams of mercuric oxide. Mercuric oxide is basically a compound with mercury and oxygen. So 100 grams of mercuric oxide decomposes into a certain amount of mercury. And the question is how many grams of oxygen must be produced in that reaction? So just take a step back. You start out with 100 grams, you're going to end up with 100 combined. So if you come up with 92.61 grams of mercury, 100 minus 92.61 is going to be the grams of oxygen. So 7.39 grams of oxygen. Okay, let's take a look at our second law. I have a marble statue above in this photo and a piece of coral from the ocean in the bottom. Are these the same? And you would need to know what they're composed of. They're composed of calcium carbonate, CaCO3, and even though they look different, they are actually both the same composition. They may have formed together in a certain pattern or a certain array, just like sometimes certain compounds will form beautiful crystalline structures. Some may not join together at all. For example, gaseous water versus a snowflake. This is the law of definite composition. The marble above and the coral below both are CaCO3. So no matter the source, a compound has the same elements in the same parts by mass. So I'll go through this more on the next slide. Say you have 100 grams of calcium carbonate. In that sample, because you have calcium, one carbon, and 3 oxygens, and they weigh a certain amount, you could look at the periodic table to see what they weigh. But what you will find is in 100 grams of calcium carbonate, 40 grams of it is calcium, 12 is carbon, 48 is oxygen. So that's useful to take a sample and compare it to see if you do have those ratios and see if, for example, oh, do you have pure calcium carbonate and it's exactly that, or is it impure? Maybe it deviates from that. And so you don't always have 100 grams of a sample. So what's more useful to use is mass percent. So no matter the source, in a pure sample of calcium carbonate, you will always have 40% calcium, 12% carbon, and 48% oxygen. Moving to atomic theory. In the early 1800s, John Dalton came up with a theory of what made up matter, what composed what matter composed of. So this was an interesting theory because we can look at it today and see that 3 out of the 4 that I'm listing here have been disproven. But I really want to highlight that to make advances in science, you have to start somewhere. You need someone brave enough to come up with some ideas. You may have some ideas about something, starting a company, some new technology, and may feel courageous enough to go with it and try it and put it out there. It may take off or it may not, but I respect that people do take that chance. So good on Dalton for taking a stab at this. He started with the notion that all matter consisted of atoms and that these were tiny indivisible particles of an element that cannot be created or destroyed. Remember, this is the early 1800s. They don't have the information or technology or microscopes or other instruments that we have now. So they could not see beyond matter. So this was a reasonable assumption. We know this is not true today. So you guys can think of which of the 3 are not correct. You probably know that atoms are made of protons, neutrons, and electrons, which get discovered 100 years after this. Atoms of one element cannot be converted into atoms of another. Think about that. Is that true or false? And this one is not true today because we've seen nuclear fission and fusion, where you can combine different nuclei and basically change the number of protons in an atom. That's how you change from one element to another, it's the number of protons that are different. So you can join different nuclei, or some of them can break apart. The third, atoms of an element are identical in mass and other properties. This is not true because we know we have isotopes, and we'll get into that. The last one is true. Compounds form or are a result from chemical combinations of a specific ratio of atoms. For example, 1 carbon and 1 O make carbon monoxide. 1 carbon and 2 O's make up carbon dioxide. Okay, fast forward 100 years. It took 100 years to get some good experimentation going to discover the electron. This is just an evacuated piece of glassware, and that means the air has been sucked out of it. There may be like a particle of air in there, or one of the components of air. And what's in this is an anode and a cathode, which are basically metals. And what you can do is electrically excite this, run a current through it, and what is observed is this glowing ray that can hit this end of the tube, and you can see a light up. So what was interesting is when they passed this through a magnetic and electric field, they could see that that glowing ray was bent. So whatever was making up this glowing ray, it was charged because it could be moved by this electric field here. The other thing that they found was that no matter what the anode or cathode was, if you flip those out, you still get the same result, meaning that whatever is occurring here, whatever is coming out of these metals and producing this ray, it's found in all matter. This was the discovery of the electron. So basically, the electrons are coming off, being excited here and moving, pulled out of an atom and moving through and shining up here. Okay. J.J. Thomson wins the Nobel Prize for this work. He identifies electrons, says that they're very, very lightweight and negatively charged. This was huge because remember the school of thought before. The idea that Dalton put forth was that the atom was the smallest particle. The mass of an electron was 1/1000th of a hydrogen atom. So that pretty much blew the minds of a lot of scientists at that time. He couldn't find separately the mass or charge, but he found a mass charge ratio to be this number, negative 5.6 blah blah kilograms per coulomb. That comes into play later. What's cool is this is how the old school CRT TVs worked. I grew up with this type of TV, and basically you have a coil that is made of copper, some metal, and it directs a beam, just like we saw with the evacuated tube, onto a phosphor coated screen that can emit colored light. And the electron beam paints the screen about 30 times per second to help us see an image in color. Second experiment, this helps us determine the charge of an electron. This is actually shockingly simplistic in a sense and gives the charge of an electron to very, very high precision related to the known number today. So basically there's a chamber here. There is a spray bottle filled with oil. Just think of canola oil at home, and you put it in a spray bottle, you spray these oil droplets, then you let it go through a little teeny funnel and hole to separate out the droplets. And then over here, there's an X-ray source, and you shine an X-ray to hit and kick out an electron from an particle in the air. And that electron lands on a water droplet. Not a water droplet, an oil droplet. So there were a bunch of, sometimes one would land on it, 2 electrons might land, but they found multiples of this one number. And just by using the motion and an electric field, they could calculate the charge of a single electron, shown here a negative number in coulombs. So electrons are negatively charged. Using that number, the charge, and the mass over charge number from J.J. Thomson, you can cancel out the Coulomb charges and end up with a mass of the electron. That's how the mass of the electron was discovered, 9 times 10 to the minus 28 grams. Super, super teeny tiny. We say it's negligible compared to the proton and neutron, but there still is a mass. It still is a particle. So a whole new light is shed on atoms. This is really interesting. Think about where they're at now. They know that there are electrons. These are negatively charged, but mass is neutral. So what's contributing to the positive charge? And also what's contributing to the mass if the electron has such a tiny mass? So notice that this is happening over time. This is happening with scientists across the world. And that's what it takes, even today. Discoveries made today, the same. J.J. Thomson puts forth another model, which ends up being wrong, but that's part of the game. You need other people to bounce ideas off of, and you try and you come up with something, and eventually progress is made. His model was that the whole positive charge was kind of diffused throughout the whole atom. This is called the Plum pudding model. And electrons are just spread out throughout. It took Rutherford and his graduate student to discover the nucleus and where the positive charge really is. It's not diffused throughout. It's actually dense in the center. And this experiment basically is taking a radium element, which is radioactive and can emit off an alpha particle. An alpha particle is like a helium nuclei. Basically, an atom of helium you could think of being shot towards a piece of gold foil. So they're using the gold foil to see, okay, let's see where this positive charge is. Let's just see how this behaves. Based on the Plum pudding model, everything should go right through. Kind of like throwing a ball through a sheet of paper, like a big piece of butcher paper, and you throw a heavy baseball through it. That's what was observed. But every once in a while, one would reflect and bounce back. So what that I remember reading this, and the graduate student was super excited, ran to Rutherford and told him the experiment results. And what they realized, there must be something dense in here. So it's like a baseball now hitting something dense and bouncing back. And that's what led to the discovery of the nucleus. The atom is mostly space occupied by electrons, not dense. The dense center is the nucleus with the positive charge and mass. The positive particles called protons. But what about the rest of the mass? We now come to 1932. So quite a bit of number of decades have passed since the discovery of the electron, and we're now in the United States. This is an American scientist, James Chadwick. He ends up identifying the neutron, uncharged particle in the nucleus with a mass similar to the proton. Let's sum it all up. The atom is electrically neutral, and that's because it has a positively charged nucleus, the positive charge from the proton, and negatively charged electrons. Look at this. This is the approximate size of an atom, 1 × 10⁻10 meters. This teeny tiny dot in the center is the nucleus, about 5 × 10⁻5 meters. So if we pull that out, blow it up, we see the protons here in purple, positive charge neutrons here in gray, and the electrons are in the space around. Electrons give atoms their size. So as you go across the periodic table, look at the atomic number, say you're at atomic number 4. That guy in a normal situation will have 4 protons, 4 neutrons, and 4 electrons around the nucleus. As you start moving across and down the periodic table, you need to fit more protons and neutrons, which will stay in the nucleus, but you start running out of space for electrons, so then you need to keep building around and around. So as you go down the periodic table, the size gets bigger as you go down a column. Okay, I'm going to end here, and we'll take a closer look at atomic symbols and isotopes next time.